thank you very much for the introduction, Carl. Thank you for the effort to wake up on the day after the evening when the bar was open till whatever, 11, I think. I'm very happy to see all of you here. So yeah, my talk is called, you all can read slides, so I'm not going to read the slides, I will just move through them forward and that would be it. So this is my professional background. I work on all kinds of VMs in my life, on some of them for longer than 6 months. The first one is a GVM, probably nobody knows about it, except some people who work on the GVMs sometimes. And then I worked on the V8, which was a JavaScript engine inside the Chrome, and then I worked on the Dart VM, and I worked for some time on LuaJIT. And the reason I worked on LuaJIT is because I was working with people who use Torch. And the Torch is like linear algebra and it's like machine learning framework built on top of Lua. And they were interested in pursuing some issues within LuaJIT and fixing crashes and stuff like that. So I was doing that for them. So don't expect that I'm going to deliver you a deep internal insights into the LuaJIT today, because I'm not the person who implemented LuaJIT to begin with, and probably he will be more well-positioned to give this insight. Instead, I will give you an overview of things that I consider being interesting inside the LuaJIT that when I was reading the source, I thought that these things are interesting. Okay, so I just want to check if people know Lua to begin with, because it will make some explanations easier. So how many people in the room know Lua, at least a little bit? Okay, it's actually a relatively well-known language. So I will give you a very quick introduction to Lua for the people who don't have an experience with it. So the Lua is a dynamically typed language, which is like JavaScript, but a little bit better. Depends on whom you ask. So it has dynamic typing. It has like numbers, strings, booleans. It has the table, which is the key value dictionary, and it has closures. Simple. And you can see it has a kind of algo-like syntax instead of C-like syntax. So the tables are key value dictionaries, where key can be of any type, unlike in JavaScript where key can only be a string. The syntax like this is just a shorthand for a syntax like this, where you have a key with a value x string, or y string, or a number, or even another table can be a key as well. The number type is there is a single numeric type. It's double precision floating point, like in JavaScript. So this is all of these values are considered numbers in Lua. And there is a feature called meta tables, which allows you to alter the behavior of tables. So you can set a meta table for a table, and this will change how the indexing operation and the creation of like assigning a value to an index works. So for example, here I say that when you try to get a key from the table, you will print the key and return 0 always. And here I say that when you try to put a key, you want to associate the key with a given value, then you will just print this and do nothing else. So if you try to do this, you will get printed index some key and then 0, because it returns 0, and then if you try to assign some value to 42, it will print new index 42 some value. That's basically it. It's very trivial, very simple. And it can also behave like a prototype chain in the JavaScript. If you assign to index instead of a function, you assign a table, then instead of calling it, it will just, if there is no such key in the table, it will look it up on the index table inside the meta table. So here I assign the table which contains x to the index method on the meta table for the table. And when I try to look up x and x is not in the table, it goes to this table and returns 42. So yeah, if you ever wrote any JavaScript, it should be obvious how this works, or Smalltalk also. Okay, and meta tables allow you to override things like plus and stuff like that. So you can basically override all kinds of operators. That's basically it. Let's return to this simple example here. After this whirlwind introduction, you will it should be completely obvious to you that this example is completely meaningless pile of stuff, which I put on the slides simply to illustrate that LuaJIT is a very good JIT. So if you run this example, so what does it do? It creates a table with two keys, like x equals 1 and y equals 1, and then in the loop, it replaces the value of this local variable with another table where the one component is moving forward essentially, and one component is moving backwards. So it's sum. One sum is with plus sign, and one sum is with minus sign. But okay, there should be -1 here. It doesn't matter basically. It's some meaningless stuff. What I wanted to illustrate is that if you look at which kind of code the LuaJIT generates for this loop, you will be very impressed. And you will go and write some posts in your blog and say this is the best JIT in your life, and you will never use any other JIT in your life again. So why this code is good? How many people can actually read the x86 assembly? How many people think that they can't read that this is an addition and like this is a subtraction? No, anyway. So it's all mnemonic, so it should be very easy to read. So you can see that there is no actual allocation in this loop, right? I was allocating a table here in the loop on every iteration, but this somehow disappeared. And instead, we are operating with the scalar values. So this is a holy grail for many compilers to eliminate the abstractions and do a scalar replacement, essentially. And that's why you will write the blog post about LuaJIT. Some people, after seeing this kind of compiled code, they will ask, how does it do it? And they will try to go and learn this by reading the source. And I will tell you that I'm not the kind of person who can learn things by reading the source from the beginning to the end, mostly because it's very hard to find the beginning and end in the pile of C code. Instead, I do strange things to the source. Like here, for example, I add the key to the table, which like I say, this P1 is equals to 1, and then I just thread it through the whole loop iteration. Then I look at what kind of code the LuaJIT generates, and discover that suddenly there is a whole pile of assembly coming out, and there is a table allocation here and some GC steps and whatnot. I am not very happy person after seeing that, of course. I become like, what? I thought this is the best JIT in the world, and it cannot cope with a small addition. Like, it's just the key that gets threaded and nothing happening here. So I like to ask, why does it not do something? And learning by fixing bugs, or at least trying to understand why something doesn't work. And I think this is the much better learning technique. And that's how I learned all the things that I'm going to talk about today. Because I learned them by looking why something does not work. So as an example of things that did not work in LuaJIT, and got fixed not by me, but by the Mike Paul himself, was 1 GB memory limit. So on the LuaJIT pre-version 2.1, there was this strange limit on the memory. Like you could only have a memory in the lower 1 GB of an address space, and you could not have more. So why that happened? Well, as I said before, Lua is dynamically typed, and there are various techniques for implementing dynamic typing. What was chosen for LuaJIT was NAND tagging. So how many people are familiar with tagging? Okay, more people. Okay, they're getting more and more people. I think they are reading on the phones while I am doing the talk. Okay, anyway, this is the double. This is the double precision floating point number. It's 64 bits in total, and there is some sign bit, and then there is an exponent bits and the mantissa bits. I think everybody should know that from a computer science curriculum. And the observation to make here is that there is the whole family of nans, not a number values, for unclear reasons. You can have like anything that has the exponent set to the all bits set, and then the non-zero mantissa, that's not a number values. And usually you need only one, or maybe two, quiet and signaling one. But there is much more than that. You can see there's the whole 52 bits that you have to set in the various patterns and use them for your evil purposes. Yeah. So what LuaJIT does with this observation is that it says, I have the t value, which is a dynamically typed slot. And it's the size of the double. And if I'm storing the number in it, then it's just stored directly. But if I want to store something that is a heap allocated object, then I store the pointer to it in the lower word. And then I put the type tag in the upper word. And then, yeah, that's it. That's the tagging system that LuaJIT uses. And yeah, for example, to check whether something is a number, you just need to compare the most significant word, the upper word, with this magical value here, because that's where the NAND boundary is. And then the table, for example, the table tag would be this value. It's just an implementation detail, and the pointer would be in the lower part of the double. And you can kind of see where the limit is coming from, right? You have only 32-bit space here, and I expect at least somebody to say, wait, 32-bit should give you at least 4 gigabytes, right? If we studied math well in the university. And the reason why it is not the case and why there is a 2 gigabyte, why there is a 1 gigabyte limit was because on Linux, what's the best way to allocate memory in the lower space, address space? It's to pass the map 32-bit flag to the mmap. But it turns out that the Linux people were a little bit lazy when they were implementing it, and they said everybody needs only 1 gigabyte. So they just allocate, not from the lower 32-bit address space, but from the lower 1 gigabyte space. So yeah, that's the reason why it is 1 gigabyte. Also, in some code, JIT-generated code, it would be sign extended. So it's, even if the Linux people are not lazy, you would only still be able to use the lower 2 gigabytes. Okay. So in the 2.1, the tagging scheme was changed. This part for the pointer was expanded to the 47 bits. And then the tag is only 4 bits, because that's enough to represent all the types used in the Lua interpreter. And then the upper bits should be all set to 1. So as you can see here, you can store a bigger pointers. And that satisfies most connoisseurs, but not the people who actually use ARM, because the most modern ARM CPUs expanding the virtual address spaces to a much bigger sizes. And you will not be able to store this in here. Okay. And some people might ask, why is it even a tough exercise to change the tagging scheme? It is a tough exercise. Like, I'm pretty sure people like in PyPy would like to experiment with different tagging scheme, even though they don't believe in tagging to begin with.
No, we did.
You did, okay. But you hidden the results of those experiments. Anyway, yeah, okay, good to know. So, yeah. And that's because this is how interpreter in LuaJIT looks like. It's 1,000 something lines of assembly code written by hand for each architecture that LuaJIT runs on. And you can see it's not a normal assembler, which at least helps a little bit to write it, but it's still an assembler, so it's very hard to fix, to change all the places where you have a dependency on your tagging scheme. And it's interesting that the assembler that the LuaJIT uses to generate its interpreter is actually it's the special assembler that Mike Paul written specifically for LuaJIT in Lua. So there is a Lua script which during the bootstrap parses these files and generates the interpreter. So yeah, so it parses the things and generates the C code, which when compiled and run would generate the binary blob with an interpreter inside. And this is actually a very interesting thing, which I find like kind of useful, because one thing you always have a challenge with when you write interpreters is that you would like to have certain constants embedded into your code, which only C compiler knows, because you usually write your runtime system in the C or C++, and then you would like to have certain constants there, like for example offsets in the objects. And you either have a choice of parsing the C++ code and computing those offsets, or using the compiler for that. And here, by generating the C code and then compiling it and emitting the interpreter, we work around, because like here we generate this snippet gets compiled to some blob of binary data number 10,000 something, with these constants like lifted out of it. And then when this C code is run, it just fills the holes in the generated code with those constants from the C side. And here, for example, it computes the offset of some fields and just puts it in. Okay. So when you write this in this assembler, that means like an offset of the certain field in a certain structure. Okay. There is still a small problem with this assembler, which I find a little bit concerning, is that it has no actual understanding of types of things that you operate with, which leads to some strange bugs sometimes. For example, there was a bug which I found where when it moved from 32-bit to 64-bit, because the assembler doesn't have understanding of sizes of things, there was a discrepancy. For example, this is a pointer value, but this size was not updated when you move to from 32 to 64. As a result, you are comparing the lower part of the pointer with 0 and then doing the decision based on that, which is incorrect. So it should be actually a different size. It's one letter change, but it leads to very flaky crashes. Okay, so let's talk a little bit about what's interpreter interpreting. They interpret in a very simple instruction format. It's 32 bits inside each instruction. There is a lower part, lower 8 bits opcode, and then you either have 3 operands or 2 operands. 3 operands 8-bit each, or 1 operand 8-bit each, 8-bit and then 16-bit operand. Very uniform, very easy to iterate, for example, this instruction stream. And the state of the interpreter looks like this. So you have a base pointer, which can be compared to the frame pointer in the i32 architecture. And there is like a sequence of 64-bit tagged slots. And you can address them from your instructions as registers, essentially. And that's it. That's very simple. So if you have an operation that says add 0, 1, 3, it's like add the register number 1 and register number 3 and store result in register number 0. Yes, please. Go ahead.
There are only 4 registers.
What?
How many registers?
No, it goes to infinity.
Oh, okay.
To there somewhere. So eventually it overflows some limits probably, but okay. Who knows. But from the encoding you can kind of deduce that if you have more than 56 registers, then you're in kind of trouble. And it's actually, if you try to compile a Lua program, which has more than 128 local variables, it says, sorry, cannot do that. So that's kind of a limit, strange small limits. But I mean, who seriously needs more than 128 local variables? Nobody. Okay, so the interesting instruction is call, because kind of without calls, we can rarely write any useful code. This is the semantics of the call instruction. Let's not dig very deep into it, but what it does is you specify a register from which to take a function value, and then you just call it with n subsequent registers, essentially. So on the stack, on this stack register space, you have the function followed by the arguments, and that's what it does, basically. And then you also specify the number of expected result values, because the Lua has the multiple return values, but we will ignore explanation of all these small things related to the handling of the multiple return values and stuff like that for brevity. So instead, we'll just say that, yeah, call is you take a function and pass everything after the function to the function. So one interesting thing about this is how simple the call sequence is. So you take the function and you just move the base pointer to here, and now all your arguments are in the first n slots. And that's almost it. So the only thing you need to do is somehow to put an information where to return to, right? What's the return address? And you do it by linking that to the previous frame and storing some more information. So then the way you link, you say, okay, there is a function stored here. It's a 64-bit slot with the pointer to the function and some type tag which says it's a function. But you know that here you can only have a function. So you don't need these 32 bits. And then you can stash some information there. So then you don't need to move anything around, create any additional space. You just replace the tag of the function on the stack with some additional information which explains how to return. And that's it. You're done. You can proceed executing the body of the function. Yes?
Why do you need the pointer still at all?
Because you might well, if you throw an exception where you are and stuff like that, to load things like up values, the values that you are closing on and stuff like that. So it's for various things. Like here I illustrated how the thing looks like if you're calling the normal Lua function from a normal Lua functions. There are more complicated calling things in the calling combinations in Lua. But all of them magically fit into this 32-bit encoding because the author of the LuaJIT looked at the possible bit patterns and realized that, so the program counters, because all our instructions are 32 bits, they always have the lower 2 bits 0. Okay, that's good. Now if we want to encode the different, like usually to return to the previous frame, you need to know how to shift the base pointer backwards. And so you need some delta. And the delta is always 8-byte aligned because all slots are 64-bit. So you have the lower 3 bits available for you. And then you just do the dance with figuring out how to use these bits in a way that they don't intersect with each other. And then you could encode the delta and the PC as the upper parts, and the lower parts tell you which type of the return you should execute. And I'm not going to talk about most of this because they're really specific to Lua, but I just find this encoding very tight, very elegant. Yeah, I show you how the return to the Lua frame. So here you can see that there is actually no delta encoded. Like you can ask, how do you reconstruct the base pointer? And you reconstruct it by looking at the caller of yourself, right? You just look at the return address of the previous instruction of the return address. And it was a call instruction, which says that the base of the call is in this register. So then you just subtract the base of the call, and then you are back to the previous frame. So you don't even need to encode the caller frame pointer anywhere. You don't need to store it anywhere. Again, very observant, I would say. Yeah. And there is a very interesting type of frame in the LuaJIT. It's called the continuation frame. And it also surprised me with its elegance, so I would like to talk a little bit about it. So the continuations allow you to specify actions to perform when caller returns. And they're used in various things. Like, for example, if you have a bytecode instruction which compares two values, like if is equal A and D, then you jump to the target. As I said, there is meta methods in the game here, and you can overload the equality comparison as well. And how would you implement then handling of the meta method? Because you need to, so what it has in equality meta method? You need to call the meta method, execute. It can be a Lua code as well. Then you need to return, and then you need to actually decide whether you need to jump or not jump, depending on the value you returned. So one potential implementation would be you have an interpreter which is stopped here, somewhere inside the implementation of a bytecode is equal. And then you have a nested interpreter which starts executing the meta method. And then when the nested interpreter returns, you will branch on the result of the nested interpreter. And this is kind of complicated because you suddenly have these nested interpreters and stuff like that. You have to, if you need to traverse the stacks, you suddenly need to traverse two stacks in parallel and stuff. It gets really messy. Instead, what you do, you use continuation frames. So some stuff a little bit on the side, but it doesn't really matter. So you say, so this is your current frame, and then you put a small chunk of information here which will be saying when this frame, so this will be the frame for the meta method call, executing the things. And when this returns, there will be a pointer stored here which says, basically it's a part of the interpreter, the continuation of the bytecode implementation for equality. And it will just execute it and do the branch on the target thing. So you have the small action here specifying what to do when this returns. And then you don't need to actually have nested interpreters because you captured the continuation of the interpreter there. So is this clear or not? Yeah, okay. It was a rhetoric question. Let's talk a little bit about dispatch, and or it should be say dispatch or something. I don't know in British English. So, and when I was giving this talk to my colleagues, as a dry run, some of them became confused because when you say dispatch to the people who work on dynamically typed languages, they immediately think about method calls. And I'm talking more about the interpreted dispatch. So the interpreted dispatch is very simple and like something that you expect from the interpreter. You have a table of handlers for each bytecode in the system, and then you just go there. Nothing novel here, really. And one observation that anybody implementing the interpreter should make here is that you can replace handlers, and you should be replacing handlers to implement various things like debugging and stuff. So some people come up with completely messy schemes for implementing debugging and things like that, but you cannot just replace the functions you store in this table, and that's it. And you can even implement profiling using that. You just, from the signal handler or from another thread, you replace the whole table with a callback that does record that you had a tick and stuff like this. And it also allows you to do the recording. And the recording we are slowly getting to the JIT part now. So the recording is the recording, yes. Anyway, so how many people know how tracing compilers work in the room? Okay, some people know, some don't. Anyway, so you want to discover hot instructions that start your trace, and you want to start collecting, basically recording every bytecode that is being executed after that. So the way LuaJIT discovers hot instructions, hot like loop headers and hot function entries, is it does hot counting on basically all of these bytecodes that either start the loop or bytecodes that start the function. It has separate bytecodes for this. And the way it does hot counting is very interesting. So here is an assembly code, and here is actually how it looks like in C if I like decompile it to C. So you have a table of some fixed size, which is a power of 2. And then you just shift away the bits which are always 0 in the program counter, and then you mask it with a table size to create this essentially hash table. And then you increment, or rather decrement the count in this table, and that's it. So it actually does not know precise counts for each loop header or each function entry. Instead, it meshes them all into this table, and once this count reaches 0, it goes into the tracing recording mode. And the table is rather small, actually. It's only 64 entries, which is, I found it very interesting. It leads to non-determinism, because depending on how you allocate your bytecodes in the memory, they can clash in different ways, and then you end up optimizing something before something else. But it's not all our life non-deterministic, so that's not really a big problem, it turns out. Yes?
Try increasing that.
You can try increasing it, yes.
And does it have any interesting effects?
It just changes how it optimizes things in the order, and that's it. Yeah. I mean, it seems to be sooner or later because it stops counting at the instructions that were optimized. So sooner or later, everything that is hot, even if it clashes, will be optimized. Right. Yes. Right. So, okay. Now let's talk about recording. So recording is what starts when you discover that you found a hot loop header or function entry. So I will give a tracing 101 now, because Carl said it would be good if you do the tracing 101. So tracing 101 looks like this. You start with a dot, and then you add some underscores to it. No, so this is the hot. It became much clearer now. So you start with the hot instruction, and then you start just recording instructions that you see. Sooner or later, you arrive to the place where you have branching of some sort. It's maybe based on the condition, or it might be just entering some function. And you never know if it will be ever the same function if you come there next time. So it is also kind of branching. And then you always, obviously, the execution, we are not writing in some strange non-deterministic programming language where execution can go all directions. The execution always goes one direction when it arrives to this branchy path. So you record that you took the turn to the right here, and then you continue, then you arrive to the next branchy path, and then you always just record the path that you actually have taken. And sooner or later, you arrive to the completion of some sort. It can be just you looped backwards to the same instruction which you have seen before, or you have, like this was a function entry and this is a return from the function. And then you say, okay, I have this trace. Then you linearize it, and then all these paths that you could have taken but not taken, they become guards in your code. So you say, when you execute this linearized sequence and you arrive to this decision again, then if you check the condition, and if it holds, you just proceed forward. And if it does not, then sorry, not sorry, cannot continue, have to go out. So, and the thing is, if you are taking one of these side exits, a lot of times you do some counting, and then if you take it enough times, you start tracing from there, and maybe you will loop back to here, or maybe you will loop somewhere else. And then you have such a maze or spider web of traces, and that's basically tracing 101. Yes. Did this become clear, or do I need to do this several times?
It's the priority animation.
Well, it's handmade, artisanal animation. Anyway, so did it become clear if you didn't know how tracing works? Okay. Okay. So I will explain how recording works a little bit in more detail. So you have the interpreter here, and you have the recorder here. And the interpreter has its state in the stack. And the recorder has the mirror of the same state, but instead of the concrete values, it stores SSA references. So it's like an abstract state, essentially. And then when you do something in the interpreter, like here you say, I want to add register 0 and register 1 and store the result in register 0. Then if you have number here, so this is register 0, register 1. And here you have SSA reference number 1, SSA reference number... So okay, I say SSA, how many people know what SSA is? Okay, good. It's... how is it? No, anyway, static single assignment form. So anyway, it's a form of intermediate representation. Yeah. What I was talking about. Yeah, so you have the SSA value 1, SSA value 2 in these corresponding slots. Then what you do, you say, okay, we are trying to add things. So I would generate the intermediate representation operation, which adds 1 because it's at 1 here and 2 here, which adds 1 and 2. And this will be SSA value 3, and I stored it in the register 1. And that's it. Basically, I have a yes, please.
At the same time, it also always is the addition of the interpreter's value stack, right?
Sorry, what again?
At the same time as doing the recording, it will also always do the addition of the interpreter.
Yeah, of course, yeah. So what actually happens, you have a hook called before this executes. So it sees the state of the world before executing it, and then once this completes, once it emits it, it returns to interpret, and the interpreter just does what it does, interprets. Okay, and if you have then subtraction, then you do again like the same. You say, okay, I want to subtract constant 1 from the register 1, so I take 2 from here, then constant 1, and I generate the subtraction from the value 2, and I store the result in the register 1 here and here as well. Okay. So let's talk a little bit about IR, because IR is a very important part of any compiler. This is how the trace object looks in C code. And I know that many people don't like C code, but please bear with me. You have to like C code if you want to look in the LuaJIT sources. This is the IR, and you can see that IR is stored by value here. So this is an array of IR instructions stored in memory by value. And there is some magic going on here which is in this comment which says biased with ref bias. And it might be a little bit cryptic statement, so I will demonstrate what it actually means. So IR instructions, the intermediate representation instructions, are referenced when you work with them by references, which are just 16-bit numbers, which are indices in this array. But they're not actual real indices. So you organize IR in a very interesting way, so that I will just better show you the picture instead of the comment. You have all non-constant instructions going forward, and all constant instructions going backwards. So like in the sense of a butterfly. And your IR array pointer is actually somewhere there, in where the queen lives. And you have to add this bias to it to find the middle of this array. So this is what it's biased with ref bias means, which allows you to quickly check whether the reference is pointing to the IR instruction which is constant or not constant, for example. Yeah, so this is how the IR is organized in memory. And actually the beginning of an allocated array is somewhere here, and the IR pointer is somewhere, even, it's not necessary, so IR0 is not necessary even in allocated memory. So just some little bit of pointer magic. Okay, so this is how IR instruction looks like. It's a 64, you already heard 64-bit a lot in this talk. So this is again a 64-bit value, and that's it. There is no complicated pointers going backwards and forwards. That's all there is to the IR instruction, 64-bit of information. And sometimes when field becomes unused at some optimization stage, it becomes reused for something else. I will demonstrate it now. So for example, all IR instructions of the same type, of the same opcode, are linked together using this field here. So that if you need to quickly find all the stores, you just iterate this chain of instructions using this link here, which allows you to quickly check some preconditions. Like if you want to forward store to load, you want to check if there is interfering things. And for that, you just need to iterate IR using these links and stuff like that. Or if you want to find the, if you do common sub-expression elimination, you obviously want to find the last emitted operation with the same opcode and look if it matches. You can just check because you have the beginning of this stored in some array on the side. So this is a very cool thing. This link is only used when you actually generate in IR and optimizing it. But when you proceed to generate code in the backend, you no longer need it. So it is actually used for the register allocator state. And that's the number of the register number, then the stack spill slot number. Then there is a space, 8-bit space for the opcode of the IR instruction, and then the type of the opcode, type of the IR instruction, because you can have a load which loads a number, or you can have a load which loads an integer, or you can have a load which loads something else. And then this type specifies what you're actually doing for those instructions where the type matters. And then you have references to the IR instructions which are operands. And it's 2 operand instructions always. This can be a constant or immediate. So you can make an interesting observation that you can embed immediates into one of these operands, which is less than the ref bias, because then it will be perceived as a constant in the IR when doing some operations with it. And also you can see that there is a space to store 32-bit pointer somewhere or 32-bit integer. And you can also see that you can observe, if you're really following what's happening here, is that there is no space for 64-bit pointers again. So the IR is not 64-bit ready. So right now somebody is refactoring this whole thing to have a space a little bit for the 64-bit values there. Anyway, so yeah. Another interesting thing is that when you work with the IR, you want to pass around the references into the IR around. And when you pass the references into the IR around, you actually don't pass the 16-bit reference. You add the type of you load the type of the IR instruction and you store it in the reference itself, which allows you to do some checks without looking into the IR array. So for example, when you create this reference, it can be pointing to the instruction which produces a number. And you just put this information into the reference itself. And if you want to check quickly whether this is pointing to the instruction that returns a string or not, you just compare this. Oh, it returns a number. I don't have to do anything. So it helps you to quickly check types of the IR instructions without actually looking at the IR instructions when you do optimizations. Okay, so we kind of want to talk a little bit about this pipeline from bytecode to SSAIR now. So as I said, you interpret and then you specialize. I haven't said anything about specialization. Then you pipe it through some sort of optimizations, and then you get your IR. So we will talk a little bit about this part. We kind of talked a little bit about that part. So this is C code. This is C code. This is a statement. Which produces IR for the len operation, the length operation in the Lua code. So there is a special bytecode because there is a special operator to take the length. And what it does is that it asks, okay, is my the operation operand, is it pointing to a string? And then if it's pointing to a string, I just need to emit the load of a field, fload, from the offset in the string, and that's it. I get the length of the string, right? So that's what it does. It says emit this IR for doing the operation, the field load on this operand and this field. And then there is some stuff. Maybe it's a table. Then if it's not some compatibility mode, then whatever, emit some special call to a function to compute the table length. Or else record the call to the method method, because it should be a method method call. Yes. Yeah.
Should there be a type card or something in the T? Does the T-ref is true?
No, here it's already all type guarded. So I will talk a little bit about it. So because this is already, so here you ask T-ref is true, it means that the type of the value is already a string. The LuaJIT very aggressively specializes on types. So there is, if it's already a string, it means there is already a guard of some sort. I will talk a little bit about this later in the amusing parts section. So this emit IR operation here doesn't actually immediately add the instruction to the stream of the instructions in this array. Interestingly enough, it passes it to the fold engine, which basically all the IR you emit is going through this sausage factory, which meshes instructions and does all kinds of classical optimizations. And only if it manages to survive until the very end, it gets added to the instruction array. So unlike some other JIT compilers where the recording pipeline just continuously records and then optimizes, the optimizations in LuaJIT are applied continuously. So, and the fold engine is a gem in its own right. So it's done very interestingly. So you have the C file with some macroses inside which say, they specify the fold rules. So here fold rules says, if you have a field load opcode with the first operand being the string allocation opcode, and then the second operand being the this field index, which is the length field in the string, then you apply this folding function to the instruction. And then there is a preprocessor which parses this file, finds all of these headers and these headers, and builds a hash table with this being a key and this being a value in this hash table. And then the folding engine is essentially the big fixed point loop which takes the instruction that was passed to it, and then it starts creating keys from it by taking the opcode of instruction and opcodes of the values, meshes them together, looks up if there is a folding rule, applies it. And then the folding rule can either return an existing instruction, or it can say stop folding, emit this instruction, and if it doesn't say stop folding, then the folding will continue until the fixed point is reached. If there is no rule that matches concretely, then there is also some wildcards. You can say, if the first operand is this, but the second operand can be anything, apply this folding rule. So it's very nice. It allows you to, instead of writing this code by hand, which checks all these types, you have some automatic thing that does it. Yeah. And because it's generated ahead of time, you can select the hash properties in such a way that you have a nice hash table for lookups. So yeah, here the fold just says if you have a string allocation, then obviously you know the string length. So just return the part of the instruction that allocates the string that is equal to the string length. That's it. Yeah. So in the fold engine looks as an entry gate that works as an entry gate to different optimizations. So for example, if you have loads and stores, the fold engine will pass them to the store to load forwarding or load to load forwarding. Then there is a dead store elimination as well there. And then there is a very interesting optimization called narrow, so Lua has only the single numeric type. So you would like in some cases to narrow it down to the 32-bit integer. And that's what this optimization is about. Then there is some bound check elimination, and then there is some common subexpression elimination, which is quite simple because you just look at the opcode and then two two operands, you can all mesh it all together and just look up the equal instructions, if it allows the common sub-expression elimination, because some instructions obviously don't allow. So once you reach the end of the pipeline, you do some optimizations over the record. So once you finish recording, you reach the end of the trace, you can do some dead code elimination, and you can do the thing. So if you are running on the architecture which doesn't support natively 64-bit values, you do splitting optimization, which is taking 64-bit operation and splitting them into double 32-bit operations. And then there is allocation syncing, which we maybe talk a little bit about later, actually not, but maybe in the couloirs or in the background. Anyway, I would like to talk about the loop thing here. So once you reach the end of the recording, you would like to create a loop out of your code so that when you start executing it, you can just loop inside the trace. So I would illustrate how this works on this loop here. So you have some sum variable, and you iterate some array from 1 to n, and then you sum things together. So yeah, looks pretty simple. So this is how the bytecode for this loop looks like. So you get so this tgetv is a get value from the table based on the variable index. And then add double vv means add two variables, and then there is a loop bytecode which loops backwards, depending on the state of the iteration, which stored in the 3 registers, starting from R4. So here's like decoding of this into some readable form. So this loop bytecode is the most complicated one. So you have an index variable which corresponds to the current iteration, and then there is a step stored in R6, and then there is a limit of the loop which is stored in R5, and then you just do step, compare, and then there is, so actual value that is visible to the user code is a separate register, so you copy it there and then you jump around. So R7 is the I as I stands in the user code, but the actual loop iteration is hidden. Okay, let's now do a little bit of tracing. So there is a small trouble here, so you cannot see due to some size constraints. Okay, the power of the HTML. So can you read from the back what this says? Okay, good. So this is the frame state at the execution of this code. Now we'll start executing it. So actual recording looks at the header of the loop first to detect how it started. And then it does some magic with initializing the initial state. Like this is I value, which is, you just load it from the frame, right? So you just, when you enter the trace, you would load it from the interpreter state. So that's what it says, load it from the interpreter state. And then this says load the limit from the interpreter state and do some comparison on the limit. So the reason why LuaJIT does this strange stuff that was not anywhere in this code is to check that the limit of the loop iteration is within like 32-bit bounds. Then you can do some simpler stuff later with eliminating bounds check and stuff like that. So let's ignore this magic for now and just say that let's concentrate on the fact that it just loads the state from the interpreter using this sload stuff. Then you load the current iteration variable because you want to execute this operation which gets the value at R7 from the table at R1. So you need to load R1 from the iteration, from the interpreter state, which contains the array, and then you just do the load of the size of the table from the table. Then you do bounds check using the iteration variable. So you can see it already figured out by looking at the loop. So the loop was from 1 to n, stepping +1, and then given this, you can just check the size, the end of the iteration is not exceeding the bounds of the array, and don't do any other bounds checks. Then you load the actual array which contains the backend storage for the array contents, and then you create the reference into this. So because it's the IR is 2 operands, you cannot just say load this from this well, you can say, but anyway, so you just create, I confuse myself, you can say that, but you have a separate instruction for that, which creates a pointer essentially into this array at the given index. So this was, again, the current iteration. And then you do the load from this address. And this is what you need to do to execute the table get, given the numeric index. And then you need to do an addition on the sum, and yeah, actually the sum should say sum here. You can see that there is a small discrepancy. You load it, and then you add, and then you store it again here, and then you reach the end of the loop, and that's where you increment the loop counter, and then you check whether the loop counter is still less than loop limit. Loop limit is here, and that's it. That's the end of the trace. So, was it clear? Why I need to do this again? I think there are 3 repetitions is usually good enough. Yeah, so this is how the IR after recording looks like. You can see that there are actually more things recorded. Like, as I said, things are aggressively specialized on type. So here, for example, it says, when I load something from the interpreter state, it must be an integer. If it's not an integer, this will exit. So this thing here says this will be a guard which checks something and will exit if it's not. So here it checks that this is an integer still. And this says it should be a table because we are going to load stuff from there. So it's all very aggressively specialized based on types. Now we would like to create a loop out of this. The thing that you can loop around and never exit to the interpreter until the very end. So the way you create this loop is you take the recorded intermediate representation and you start replaying it again through the whole optimization pipeline. I think the loop was executed the second iteration. So, for example, you want to execute again this instruction. Now you're basically doing the abstract interpretation. Instead of the bytecode, you interpreted the IR. So if you want to do the load from the interpreter state, you know that at the end of this, you had the interpreter state like that. So you just need to find the 6th thing here, and that's it. So it's 1. So replaying this is the same, so you don't need to replay it. You can just reference this instruction. So then you want to do a comparison. So it's comparison with the 1 here, but you need to look now here because you replay it. So it's essentially substitution. So here 1 was substituted with 1, which means it's still 1. And this comparison is the same as this comparison, obviously, because it has no side effects or anything. So it's the same thing. So now 2 is substituted with 2. And then the same with the load of the interpreter state at the slot number 5. It's just, here it changed. It's no longer 1, right? So like there you loaded it and it was 1 because this is the loop iteration variable. So when you, on the second iteration you load it, it must be the one updated on the previous iteration. And the update was here, addition of 1 to number 3. So you say that 3 on the second iteration is substituted with 12. And then you continue doing that, so the load is obviously the same. You pipe these things through the same folding engine which works when you record normally. And it does like it sees that there is no interfering stores to this field, so it just can forward it. Then the bounce check is the same. This is the same. Now you want to create the reference into the array. And one thing did not change, so the 7 is substituted with 7, but 3 is substituted with 12. So it is no longer the same thing. So you need to emit it as a separate instruction, and you continue. The load again is the different thing, because here it was referenced in 8, and 8 is substituted with 15, and so forth, so on. The addition is obviously because you look at the state, like 10, you find it here, it's 11, so it's 11, but 9 is 16, so it's a separate instruction again, and so on. And then you reach the end, and now what you want to do is to loop this part around. And for that you need to know, yeah, yes?
So let me ask the dumb question.
Yes.
So the bit on the left is the loop header.
Yes,
You're gonna
it will
execute
become now the loop
yeah,
header,
and
yes.
The thing on the right is the loop body,
Yes,
which you're
yes.
going to execute many, many, many times.
Yes.
You've been able to just really quickly generate it.
Yes, yes.
Right, I see.
That's what you want to do, yes.
Yes.
So essentially, we are doing the loop peeling here for
Yeah.
in the sense. And now you want to loop this part around, and for that you need to compute the phi's, like in a normal system. So you look at the state, you look at some other things, you look at the state which you currently have, and you see the difference, and that's kind of the phi's. It's a little bit more complicated than that, but this is how it looks like. And one interesting thing here, which is completely mind-bending to the people who work on the normal compilers, is that the phi's are here and not here. And these things are referencing actually through this. Yeah.
Can you explain phi?
How many people know? Well, people were saying they know what SSA is. So the phi is a Greek letter. Okay, so the phi is a phi. Okay, how do I explain that? Okay, can I use that? Or we will be built separately? No. I will. Okay.
You're doing a portrait of
Don't move. Yeah. So. That's how you all look to me. So, so you have some. Okay, I will explain this in terms of basic blocks and stuff like that. I will not explain it in terms of basic. So this is your loop body, and then obviously you can loop around or you can exit the loop, and then the loop body is entered from somewhere here. So here you use some things like variables. Let's explain it simply. And there are obviously variables that come on this edge and variables that come on this edge. They're different. And you want to encode this somehow that here you refer either to the state from here or state from here, depending on where your control is coming from. And in a single static assignment form or static single assignment form, you do this using phi function. This is how the letter is spelled. So you say Z is a phi of x and y. And that means on this path, there is a x floating and flowing, and there is y flowing on this path. And here you merge them. So because here it was the same, in the source code, for example, it was the variable v, and then the state of a variable v here is a phi function of these two. So did it become clearer? Or I need to draw the... This is a phi function in the body. Anyway, so better hide it from the camera. Okay. So, as you can see in the classical portrayal of the phi function, it was at the top, but here it's a little bit at the bottom. So it's a little bit confusing when you read things. So it's actually even more confusing because, as I was saying, this is piped through the same optimization pipeline as the normal code. So when you look at this, you suddenly realize that looking at the operands doesn't guarantee you that the operands don't change on the loop iteration because there is no phi in between, actual phi instruction. So when you do the loop stuff, you need somehow to filter out the possibility that you are optimizing through phi's, which would be an incorrect optimization because if there is a string of length 3 flowing on one edge and the length of string 5 flowing on another edge, you cannot do the optimization. So there is a small macro you need to put in the right places. And if you go through the history of LuaJIT, you discover that this was missing in various places because it's so obscure that it's kind of easy to miss when you're doing an incorrect optimization through the barrier. Okay. That also means that when you do this optimization, this thing here, it actually marks somehow those instructions that will potentially become phi's, that will become non-invariants, so that the folding can check for this and abort. Anyway, this is an obscure thing. There is also thinking of optimization, which I would like to talk about, but I don't want to spend more time than necessary. Yeah, because I have only 28 minutes left. It's basically you look at the objects that your trace is allocating, and if it's not needed anywhere except side exits, if it does not leak into the fields and stuff like that, then you can decompose it into scalar values and elide the allocation itself. And then when you exit the loop, you would allocate the object. Or when you exit the trace. Then once your trace is recorded and you created a loop from it, if it was necessary, because not all traces are loops really, then you assemble it using the assembler. Because interpreter is interpreting, assembler is assembling, optimizer is optimizing. Anyway, the interesting mind-bending thing about assembler is that it's written backwards. So you recorded a trace, and then it turns out that the most natural, the most optimal way to assemble the trace is backwards. So the assembler is written literally backwards. So here you would like to emit the test followed by a jump on the condition of the test. And you write it backwards. So first you emit the jump, and then you emit the test. So this looks very strange when you read the code, and you need to always do like this when you read it, because then it becomes more reasonable. So the register allocation technique used by the the code generator is a linear scan. And it's, again, it's a trace, so it's very easy to do linear scan. You go backwards, so you see the uses or last use before the definition. So you kind of, it's very trivial to do the allocation. It might be hard to do the good allocation, but let's not go into there. It's a whole big area. And that's the end, not actually the end. I just want you to laugh a little bit. No, let's talk just a little bit about how the things get decomposed into the IR for the examples. So one big problem for all kinds of dynamic languages is doing the loads of the fields from some dynamic places like table, for example. Here you want to load something from the table. Like yesterday you heard that the self uses all kinds of things, like, or the day before that it uses maps to optimize this case. So what LuaJIT does is that it does just specialize for the place in the dictionary where the value is. So instead of doing some tracking for how the dictionary evolves during the runtime, it just, when it's used, it says, okay, load the size of this hash table, and then put a guard checking that it's the same size as we saw before. And then just take the nodes of that hash table, so it's some open addressing hash table. And then take the node at a fixed position in this array and check if it contains the given constant key. And if it does, okay, our probe succeeded, and then we can just load and continue. We will also check that the type of the loaded value is a given type. So that's it. Basically, you probe in the fixed position in the hash table, and if you hit, you are good. If you don't, you're bad. And this works if all your hash tables are created in the same way, because the keys end up in the same position. And in assembly code, it looks very efficient. Like, yeah, some assembly code. You compare the size. You can see also that the code generator is quite good at merging the expressions. Like, for example, here you say load, sum, and compare. It's very good at merging the things into the addressing modes of the, on x86 you have the rich addressing mode, so you can merge things in them. Like load, compare the size of hash table, load the array, load the value of the string, the pointer to a string, compare things together, and then just compare that the value contained in the hash table is a number, comparing the tag, and then just, if it's not a number, exit, otherwise continue. Now you have the value loaded. Of course, when you do the object-oriented programming, you have to rely on the loop invariant code motion to move all this probing out of your loops, because otherwise it's too much. If you have the code like this, which does, which sets a method table, like this is how you do object-oriented programming in Lua. You use the method tables to store the methods, and you store the fields on the table itself, and the methods are usually stored somewhere on the method table. And then you use the meta table to look up the methods. Yeah, it's like a prototype-based programming. And if you trace this, you get, so this is the part responsible for doing the method invocation, and the field load is somewhere here. So it's a lot of probing. So you need to probe that there is no value like that in the dictionary right now, because you're loading something from the prototype, essentially. Then you need to load the meta table and probe it for the index part. Then you need to probe the meta table itself for the get field methods to check that it's the same method that we executed when we saw the trace before. And it's a lot. So you can see by judging by numbers here that this is all in the invariant part of the loop because there is nothing interfering. But if there is some interference, then of course you will be probing again and again, and this is just a lot of code. So another interesting thing about the trace is that there is no reentrance. So if you either trace the Lua stuff completely or not. If you have the call somewhere which can call Lua, this is not possible. So you have to stay inside the trace or you have to exit. So if you're calling something to the API, so the Lua API allows you to define C functions which are exposed to the Lua side. If you're calling something through the API, the trace will abort there in 2.0. In 2.1, it will do a thing called stitching with these traces. So, and the reason why it is not reentrant is quite obvious. You don't want, when you return, you don't want to check invariants that you already computed somewhere. And if you're calling arbitrary Lua code, then they can invalidate invariants in an arbitrary way. So here's an example. This is the string substitution function implemented as a C function. So you have this loop doing some string substitution on the string back and forth. It's just a stupid example to show the things. And what the LuaJIT generates here is that it traces. Then there is a string substitution function, which is a C function. So it says, okay, end the trace here. Then it does call this function through, like it exits to the interpreter. The interpreter handles calling this C function. Then when the interpreter returns, it starts tracing again. And then until the next string substitution function, then it does the same dance with exiting to the interpreter and doing the C call, returning to the interpreter again, and then tracing again, and then loop around. And these traces are all independent, and then there is no redundancy elimination between them. So there is a small problem here in terms of the fact that you cannot share this trace, can't make one big trace out of this. But it's also not possible because this function can do arbitrary things. Well, not this particular, but some other one. So the inefficiency comes from the fact that you transfer the state between the traces using the interpreter state. So you have to serialize all your state, allocate the things that was sunk, for example, and then continue, and then again re-enter the trace, recheck all the assumptions that you were checking and stuff like that. Yes?
That must be built in the assumption that don't call into the C API very often, but that kind of seems unlikely.
Yeah, I will touch this at the very end, yes. So the built-in library is, you would like to implement it in a ways that does not hit this problem. So there are two ways to do it. One way is to define how you trace through the built-in library. Like you can manually say, if you reach this function, then you emit this kind of IR by hand, or you can you either need to record it manually, or there is a neat trick in the 2.1 where you can write this comment. Like you said, this is the library function for the table.remove. And it's actually very simple to implement it in the Lua itself with some magical macroses. So there is this build script which takes this, parses it, generates bytecode, patches this bytecode with some special bytecodes, and then the trace compiler can just trace through this bytecode and generate the good IR. And another way to handle it is say, no, please don't use API, use FFI. So FFI is the way that allows you to efficiently bind to the C functions. So you can call C functions directly, but not through this API thing where you can call back and forth, and you have to pass, like API is based on passing the stack essentially in, and then you operate with the stack using the functions which like pop the value from the stack, push the value from the stack. It exposes kind of implementation details. FFI you call directly with the C values. Like for example, you can say, it comes with the C parser built into LuaJIT, a very simple C parser which parses most of the C. And it can parse all the things like type defs of the structs and function declarations. And then you just can say, okay, allocate the struct with this layout, and then fill it with some structs, and then call the function. And that's all done very efficiently. If the tracing compiler sees that, it does very efficient stuff. And the assumption here is that you cannot re-enter from the C function that you called from the FFI. So actually there is, in the documentation, it says explicitly that if you re-enter, you will be punished. Because you can actually re-enter. But there is assertion. So, and another thing that he does with this FFI, you can specify the meta tables on the FFI things. But there is an assumption built in that they are frozen and can never be mutated. So this is an interesting thing with the metatables, that you can change them as your program executes. And of course you need to recheck. That means you need to recheck in the traces what's happening, and you have to assume if you see something that can potentially alias your metatable, you need to recheck things. And for the FFI, he says, you cannot do that. You cannot change the metatable once it was assigned to a FFI metatype. And that allows you to generate really tight traces. Like, for example, I showed you how the method call works on the table. And this is how the method call works on the FFI C-type. You just make one comparison with some ID which specifies what kind of C-type it is. And then if its comparison holds, then okay, everything is great. Then you just compute where the thing is inside your structure. So this is basically an inlined, it's the same method here. It just takes we're calling the method, and it just takes the field with the fixed offset. And you just compute this like pointer to the inside of the object, and you just do a load. And that's it. There's no table probing. This is all you need to do. Yeah, side traces, we talked a little bit about them. There is a problem that there is no, there is the way you carry values between the trace and side traces is not the most efficient. So if you hit the side trace, you can carry some stuff, but you can't carry all the stuff in. And when the side trace loop backs to the loop, it always rejoins at the very beginning at the preheader, which means that if you had some allocation sunk objects, you will rematerialize and dematerialize them again on the rejoin of the side trace. Yeah, here is also an interesting example about the bounce check elimination and scalar evolution analysis in the LuaJIT. So in some places in the code, you can say, apply the scalar evolution analysis to some value. But actually what it does is that it looks, if the loop is this particular loop for I equals 1 to n essentially, using this bytecode. So if you write this manually into something that looks almost exactly the same, this will be slower code with some bounce checks inside the loop than this, because he relies on in the tracing compiler, you kind of, if you don't want to do post optimizations, you have to rely on just looking the information at the start of your tracing process. Okay, and now the summary of the talk, because the talk is called What I Learned from LuaJIT, so I have to summarize what I learned actually. So elegance of the code is a double-edged sword. So I showed you that there are a lot of places in the code where things are very neatly packed together, and this is really great. This is very elegant. But if you want to change things, you will stumble and fall on your face, because there are a lot of hidden assumptions around. It's just a lot of very tedious work to carefully change things. And that's why the elegance is both good and bad, because you have optimal things, but maintaining optimal things is not optimal process. So do not fear the Reaper. And the Reaper is a preprocessor in this case. And the preprocessor, I don't mean the C++ preprocessor, I just mean some steps which you do during the build time to generate auxiliary things, like fold engine generates a hash table, the assembler, the special assembler generates the interpreter, and stuff like that. Or you find these special Lua functions embedded in the comments in your code, and you generate them as a bytecode and embed them in the binary. So don't fear this, because it actually makes life easier than just trying to come up with the clever C++ template magic to do the same things. Do pre-processing, it's simpler, it's better. Another observation is that users don't understand what makes your engine fast. And for example, you will see people all around saying LuaJIT is an amazing piece of technology which is very fast. And it is true. But then they proceed to use it using the Lua APIs. And the tracing can no longer trace anything in their code. And of course, the interpreter itself is good, but you don't get the full potential of the LuaJIT. And that's because they don't understand how the thing works. They see it as a black box. And you have to educate people who use your technology. And maybe do it politely. Then another thing that I learned from working on the LuaJIT, of cooperating with people who use LuaJIT, is that people who don't do compilers, they don't understand how tracing works. It's worse. So if you try to explain how method compiler optimizes something, how the tracing compiler optimizes something, it is much harder to explain how tracing compiler optimizes something, because the traces that are collected usually have very little relation to what is written in the program, unless you have some very simple loops. Because you can have tail recursion, which gets traced and looped around. And explaining how this got traced and looped around is not trivial. And explaining the whole guards and side exits that rejoin at the loop header, and people have their brains blown out if they have no compiler background, even if they are good computer scientists. And the final note here is that you have to search for the balance. As I showed you, there are complex optimizations and there are simple optimizations. And somewhere in between there is a balance where you hit 80% of the cases with 20% of the effort. And you are happy yourself, and your users are sometimes also happy. And the final note is that you have to bend the reality around you. If you see that something is hard to optimize, like API calls, it's not clear how to make them efficient. You just create the FFI, which is considerably more efficient, and it just educate people to use it. And by doing this, you change the rules of the game, and suddenly your compiler is the best compiler in the world. So bend reality around you, and that's the end of the talk for today.